In this lesson, we'll be looking at the chemical elements, their symbols, valencies, and oxidation states. So, after watching this tutorial, you should be able to achieve the following objectives. First, you must be able to define an element and explain how chemical symbols are derived. Okay, how do we, for example, the first element on the periodic table is hydrogen. How are those symbols derived? Hydrogen, we have silver, we have gold, we have calcium. How are those symbols derived? Should be able to explain that. Also, you should be able to identify elements based on their symbols. That is, you should be able to identify the symbols of various elements and recall common their symbols on the periodic table. Also, you should be able to differentiate elements using their English Latin derived chemical symbols. Okay. Classify elements into metals, non-metals, and metalloids. You should be able to make that classification. Also, you should be able to compare the properties, both physical and chemical properties of metals and non-metals. Also, explain the concept of valency as the combining power of elements. You should be able to determine the valency of the first 20 elements from the periodic table. Also, you should be able to distinguish between positive and negative valencies and their how they relate to electron loss and electron gain. Okay, you should be able to explain the various valencies that exist for various elements or atoms of elements. Be able to explain the relationship between valence electrons and valency. Okay. Also, you should be able to define the concept of oxidation number, oxidation states, and explain its importance in writing chemical formula. Okay, how do we apply rules for assigning oxidation number? How do you apply them? Okay, especially how we use them in naming simple compound following IUPAC nomenclature. Also, you should be able to classify oxidation numbers in simple and complex ion using rules, some specific rules. So these are the objectives. So use this objective to track your understanding of this concept. In the past, we have explained matter as we said matter is anything that has mass and occupies space. So the fundamental building block of matter are atoms. And these atoms are nothing but what? The composition of an element. Okay? So an element is like packets of atom of the same type. Packets of atom of the same type. So we want to take a deep dive into what an element is. Now, elements are the fundamental, they are fundamental substances that cannot be separated into any simpler substance by any chemical means. Okay, so they are the fundamental, they are fundamental substance that cannot be separated into simpler substance by any chemical means. Okay, for example, you cannot use the chemical means to still split hydrogen to get another species using any physical means, any chemical means. So symbols of elements, there are various symbols we have for elements. Okay, and there are three major ways with which these symbols are assigned to elements. Okay, so chemical elements or chemical symbols, they are short form used to represent elements because we use them a lot. We want to write chemical formula, we use elements. We cannot write the chemical formula using their full name. First, cannot be a formula that way. So for simplicity, elements are assigned they are assigned a symbol that is unique to them. That is unique to them. Now, the first way with which element symbols are obtained is from their first letter. The symbols of elements are obtained from what? From their first letter. Okay? So, and these are examples of such elements that are obtained from their first letter. We have hydrogen. The first letter of hydrogen is H. So that is where its symbol is gotten from. Symbol H. Oxygen, O. Iodine, I. Fluorine, F. Nitrogen, N. Sulfur, S. Carbon, C. And phosphorus, P. So it is worth noting that this must at all times be written in their capital letter. It is not correct to say hydrogen is H. It doesn't make any sense. So it is the first letter, so we use capital letter to represent the element. So you cannot write water like this, H2O. It doesn't make sense. It has to be H2O, where this 2 is a subscript of showing the number of hydrogen that is present in water molecule. So it is worth noting that when you are writing your chemical symbols, when you are writing your chemical equations or chemical formulas, you should ensure that it is written, these elements are written in capital letter. Now, the second way the elements, some elements get their symbol is the first letter written in capital letter and one other letter from its name written in small letter. Very important. For example, chlorine is Cl. The C capital letter, the L small letter. Bromine is Br. You say that it is not necessarily that it is the two first letters that forms the symbol of an element. It could be the first letter and any other letter. Like chlorine, you could say that Cl here is the third letter after C. That is, we have C, H, then L. So Cl is the generally accepted symbol for chlorine. Okay, calcium is Ca. Coincidentally here, it is the first two letters, C and A. Aluminium is the first two letters. Magnesium is also Mg, not Ma. It is Mg. So first letter and another letter within the name of the element. Also, beryllium, we say that beryllium is what? Is Mg. Sorry, beryllium is Be. Magnesium is Mg. Helium is He, which is in this case also the first two letters of its name. Neon also the first two letters of its name, and lithium the first two letters of its name. So that's the second way with which elements get their symbols. Now the third way is from their Latin name. Some elements get their symbol from their Latin name. Okay, so let's look at such elements. Okay, we have mercury. Mercury has a symbol Hg. This Hg is gotten from the first letter of its Latin name and another letter. So the Latin name is called hydrargyrium. Hydrargyrium. That is the Latin name of mercury. So the symbol H and G are assigned as the symbol for mercury. The H capital letter and the G must be small letter. Very, very important. Then sodium is from natrium, Na. Iron is Fe from ferrum. Copper is cuprum, Cu. Silver, the symbol is Ag, which is argentum from the first letter and the third letter. Tin is stannum, so that it is from the first letter and another letter, which is N in this case. So gold is aurum, potassium is calcium, and lead is plumbum. So these elements get their symbols from what? From their Latin name. Some only one letter from the Latin name, some two letters. One, the first capital letter, and the other letter always small letter. So it will not be correct to write silver as, for example, you want to write silver now, you're not write silver as Hg. It doesn't make sense. It is incorrect. It is completely incorrect. It has to be written as what? The first letter, capital letter, and the next letter within the name is a the other letter from within the name is small letter, small letter. So these are the ways with which, or these are the three ways with which elements get their symbols from their first letter in their English name, then sometimes first letter and any other letter within the name, or outrightly getting their letter, getting their symbols from their Latin name. So very, very important. Now let's look at the first 20 elements. Okay, of course, on the periodic table, you see that there are about over 100 elements, about 118 to be specific, elements on the periodic table. Now, but let's look at the first 20 elements in that order of the atomic number. Okay, the atomic number is nothing but the number of proton processed by an element. That's what we call the atom. It's usually the atomic number. Okay, it's like the identity of an element. For example, the element that has an atomic number of 8 is oxygen. Okay, it's oxygen, and nothing can, if it changes, if that atomic number changes, it cannot be oxygen anymore. So the atomic number is actually the proton number that is present in the nucleus of that atom. Okay, so it means hydrogen that has atomic number 1 has just 1 proton. Helium that has atomic number 2 has 2 protons. Lithium that has atomic number 3 has 3 protons. So all these concepts are very, very important because they form the fundamentals of how well you understand some concepts in chemistry. So you should ensure that those concepts are very clear in your head. Now, so these are all the first 20 elements. Okay, it's always good if you can memorize the first 20 elements, even the first 30 elements is good. Okay, so but even if you have not memorized it, the periodic table is always available for you to check it out. Okay, but however, I used to advise that students should be familiar with the first 20 elements. At least, if you can even try, you can memorize the first 30 elements. Okay, sometimes some students find it, because these arrangements are very important, because the arrangement of this first 20 elements is based on the atomic number. Okay, so even if you do not have access to a periodic table and you know the first 20 elements in that order from 1 to 20, you can easily count and know the atomic number of that of the element you are looking for. So there are a lot of mnemonics. There are mnemonics. Okay, there are mnemonics. Mnemonics for remembering the atomic the first 20 elements. Okay, some of such mnemonic. Let's look at one of such mnemonic. So one of the mnemonic we have is, we could say, he has large brain. He has large brain, but cannot offer full 9 subjects. Full 9 subjects. Many academic school play soccer. Soccer is not well spelled here. Soccer. Come and play card. Come and play card. So you can use this mnemonic to tie down your first 20 elements. Whenever you need it, you can easily just recite the mnemonic, and you can easily quickly figure out the elements if you don't have access to a periodic table. Okay, And some persons also use songs to tie down the first 20 elements. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. So there are different techniques with which that can help you to memorize your first 20 elements. Okay. Now, also, we have discussed the symbols. So you have to ensure that you can always remember, always write the right symbols for your elements. Okay, always write the right symbol for your elements. Now, in a minute, we'll discuss, we have discussed the atomic number, we have discussed the element itself, we have discussed the symbols. In a minute, we'll discuss what are valences. Okay, but before we discuss valency, let's look at another very important concept. Okay, let's discuss valency first before we move on to classification of elements. Okay, now, writing formula from valencies. Generally, formulas of compounds can be deduced from their valencies. What we mean valence? Valency is the combining power of an element. Okay, it's the combining power of an element. Okay, so let's discuss valency. So it can also be defined as the number of hydrogen. You can define valency as the number of hydrogen atoms that can combine with or replace one atom of an element. Okay, for example, let's go back to that table. Let's go back to this table and see the valencies of various atoms. So sometimes the valency of an atom is determined by how much electron it can lose, or how many electrons it can gain. Okay, for example, hydrogen has a valency of 1. Usually, we don't assign charges to valency. So hydrogen has an atomic number. One atomic number of 1. Okay, so say it has a valency of 1. Okay, helium has a valency has an atomic number of 2, but its valency is 2. Its valency is 0 because that 2 since it has an atomic number of 2, it means it has just 2 electrons for it to be neutral. Because for neutrality, the number of atoms and the number of protons and the number of electrons must be the same. If the number of protons and electrons is not the same, then that that atom will not be neutral. So for neutrality, okay, the number of proton and the number of electron must be the same. So if an element has, or if an atom has 2 electrons, it has 2 protons rather, and it has 2 electrons, it means it is going to be neutral. Okay, for the first case of helium, the first shell is assumed to be able to take just 2 electrons. Okay, and because it can take 2 electrons, that means it is completely fully filled. And if it is completely fully filled, okay, we'll say it has attained a duplet state. So in the case of helium here, we say helium has attained a what? A duplet state. Okay. The other elements that also behave like helium is we have neon. Neon has attained octet state. It has attained octet state. Why are we saying it has attained octet state? Because it has 10 electrons. Okay. Using Bohr model of drawing of writing electronic configuration, because it has 10 protons, we expect it to also have 10 electrons. And if it has 10 electrons, it means the first shell takes 2 and the next shell takes 8, meaning the outermost electron is nothing, is 0. That means this is fully filled. Because it is fully filled, we say valence. It has a combining power of 0. That's a combining power of 0. Okay. Similarly, we have argon. Argon also has a combining power of 0. That is, it has also attained octet. Okay, this is generally why these elements, helium, argon, neon, krypton, xenon, they are regarded as inert. Okay, at ordinary condition, they are inert because they have attained octet or duplet, as the case may be. For helium, it is duplet. Why for the rest to say they have attained octet? Meaning they are very stable at that stage because they have fully filled outermost electrons. Fully filled outermost electrons. And this is the joy of every other element. In fact, every other element that participates in chemical reactions is to attain this stability of the group zero element, of the noble gases. We call them noble gases, we call them inert gases. Okay, so they have combining power of what? Combining power of 0. Whereas the rest have their combining power from their outermost electron, from their valence electron. So the valence electron is the electron that is available outside the outermost shell of that atom of the element. Okay, lithium has a valency of 1, beryllium has a valency of 2, boron a valency of 3, carbon a valency of 4, nitrogen a valency of 5, though nitrogen can have multiple valency. Oxygen a valency of 6, fluorine valency of 7, and so on. Then we have sodium also a valency of 1, just like lithium, and potassium also has a valency of 1, just like sodium. Okay, so these are the first 20 elements and their corresponding symbols and their corresponding valences. Now, let's proceed. Now, let's look at how formulas are written. How formulas are written. Formulas of compounds can be deduced from their valences, from the valences of the components, elements, or radicals that form them, following the following rules. First, if you want to write the chemical formula of a particular combination, of a particular compound, the first is we write the symbols of that compound. We have said it in the previous video when we are discussing differences between mixtures and compound. We have specifically mentioned that a compound will have a chemical formula, okay, because it's a chemical combination of elements. So it will definitely have a chemical formula, okay? So when you want to write the chemical formulas of this compound, the first step is to write the symbols of this compound. Then the next step is you write the valences of those elements in the compound. You write it below. Then we exchange the valence. We are going to do an example in a minute. Then we exchange these valences. Okay, and from there we'll be able to derive the formula of the compound. Take for example, let's pick an element from the periodic table. Let's say we have magnesium. Magnesium is number 12. It has a combining power of 2. Okay, and let's say chlorine. Chlorine has a combining power of 1, not 7. This is a mistake. It has a combining power of 1, not 7. It's a mistake. Okay, so the same thing with fluorine. Fluorine has a combining power of 1. Okay, so not 7. Now let's go to a fresh sheet so that we can use it to solve this. Now, magnesium has been determined to have a combining power of 2, and chlorine a combining power of 1. So in the combination of, that's the first step, we write the symbol. This is step 1, and this is step 2. We write the symbols and we write their valences. Then we exchange the valences. 1 goes here, 2 goes here. Okay, so our step 3 now is what? Step 3 is we now have the required formula. So the required formula is what? MgCl2. That is, the 2 here becomes a subscript for chlorine, and the 1 here becomes a subscript for magnesium. But we don't need to write the 1 in this case. So we don't need to say this is Mg1Cl2. No. Since this 1, we just keep it that way. So this is magnesium chloride. Okay, similarly, let's assume it were to be sodium. It were to be sodium chloride that we have. The combining power of sodium is is 1. The combining power of sodium is 1, and the combining power of chlorine is also 1. So in this context, we have this. So which becomes what? NaCl. So we don't need to say Na1Cl1. No, we don't need that. Okay. How about, let's look at combination of hydrogen and oxygen. Okay. Hydrogen and oxygen. Hydrogen, for the formation of water, hydrogen has a combining power of 1. And if you check the table, you see oxygen has a combining power of 2. So in this case, we also exchange it so that we have what? H2O. H2O. So there are some exceptions in which some elements can have multiple combining powers. Okay, we're going to look at that in a minute. So these are the basic way with which elements or symbols of elements are written. The symbols of elements are used, and they are valent together with their valencies to obtain their chemical formula. So take note of those steps. Now, another point is classification of elements. Classification of elements. Elements are can be grouped into metal, non-metal, and metalloids. Metal, non-metal, and metalloids. Okay, so elements that are metals. Generally, metals have their own characteristics. Okay, we're going to discuss their characteristics in a minute. Then non-metals also have their characteristics. These are examples of some of the metals and the non-metals. Okay, so metals, generally, one of their interesting chemical properties is that they tend to lose electrons. Okay, while non-metals tend to gain electrons. Okay, so, but there are some other classification of elements that can behave both as metal. They possess both metallic property and non-metallic property. So such elements are regarded as what? As metalloids. Okay, and examples of such is silicon, carbon, and germanium. They can behave sometimes as metal and also still behave like what? As non-metals. Examples of metals include iron, zinc, tin, aluminum, and copper. Examples of non-metals, we have chlorine, oxygen, sulfur, fluorine, and hydrogen. Okay, so we shouldn't confuse hydrogen. Hydrogen is not a metal, even though it is positioned in the same group as the group 1 element. Okay, it is just positioned there because it has 1 valence electron in that atmosphere. It can equally be positioned in group 7. Okay, because it also needs 1 more electron to attain octet, to attain duplet. So, however, it must definitely be positioned somewhere. So it is positioned in group 1. That does not necessarily mean that it has the same properties as the rest of the group 1 elements. Now, let's look at the difference between metals and non-metals. So there are several differences between metals and non-metals. So some of them include: 1, solid. Metals are generally solid at room temperature, except mercury that is liquid at room temperature. Okay, and non-metals, they can either be solid, liquid, or even gases. Generally, metals are good conductor of heat and electricity, while non-metals are poor conductor of heat and electricity, except with the exception of substance like graphite of carbon. Graphite is one of the allotropes of carbon. Okay, so another property of metal is malleability. Metals are malleable, that is, they can be beaten into sheets. Okay, metals can be beaten into sheets. Okay, whereas non-metals do not have that ability. They are brittle. They cannot be straightened out or beaten into into sheets. Now, another property of metal is ductility. Metals are ductile. Ductile means they can be drawn into wires. Okay, but non-metals don't have that physical property. They cannot be drawn into wires. Also, metals have this lustrous property, that is shining property. They tend to have this characteristics shining, unlike non-metals that do not. Non-metals are generally dull. They do not have that shining characteristics. Also, generally speaking, metals have high density. Okay, and generally non-metals have low densities. Okay, so these are some of the properties of metals and non-metals. Some other important points about valency that we need to also mention. Okay, I've actually mentioned it, that some valencies can either be obtained based on the number of elements that that a particular atom, based on the number of electrons that a particular atom can lose, or based on the number of atoms it can get. Or we can still say it can be viewed based on the number of hydrogen atoms that can actually combine with that species. So valency is often related to the number of electrons in the atmosphere. We have explained that in details. Now let's look at another important concept under this topic, which is radicals. Okay, so it is also very possible for us to have two or more atoms combining and they now possess a charge. In that case, we say that kind of group of atoms possessing a charge, we call them radicals, or we call them ions. Okay, so radicals are groups of atoms that carry a charge and behave as a single unit during chemical reactions. So it is possible for some group of atoms to carry a charge. Okay, in that case, they're regarded as cation. Okay, and in the case where they carry negative charge, they are regarded as what? Anions. But that does not necessarily mean that they have to always be group of atoms for it to be. It's not only radicals that can. We can have, what I mean is there are some species that are not necessarily a group of atoms that still have charges. For example, sodium Na plus is a cation. Cl minus is an anion. Okay. We can also have, if it is group of atom like SO42 minus, is a group of atom that has a charge. Okay, so that is that about some radicals. Now let's look at some examples of radicals. Let's look at some examples of radicals and their formula. For example, we have trioxonitrate 5. Trioxonitrate 5 is NaO3 minus, NO3 minus, sorry. NO3 minus is trioxonitrate 5 with an oxidation number of -1. That is the equivalent charge of this species is -1. So usually the oxidation number of ions is the charge they carry. So you say that in this case, the assigned charge to NO3 minus is -1 because that's the equivalent charge or the effective charge it is carrying. While trioxonitrate 5 is also -1. Okay, manganese 4, tetraoxomanganate 7. Tetraoxomanganate 7 is also having a -1 charge. Hydroxide is also having a -1 charge. Carbonate, this trioxocarbonate 4 is having a charge of -2. Okay, tetraoxosulfate 6 is having a charge of -2. So it's very, very important that you are familiar with the oxidation state of these radicals. Because in a case where you have them combining with other elements, with other elements or other atoms of an element, we'll be able to know which valency are you going to use for their combination. Okay, let's just look at a typical example of that. In a case where, let's say calcium wants to combine with SO4 2 minus. So we'll take calcium as 2, SO4 2 minus as 2. Then they exchange their charges. Then to form, because we have 2 2, it's like 2 2 can also be reduced to 1 1. Okay, because it's exactly the same thing. So we have CaSO4 as the eventual formula that is formed. But however, in the case where it is hydrogen that wants to combine with SO4 2 minus, okay, the valency of this will be treated as 2, while the valency of hydrogen is 1. Okay, so they are not the same. So we exchange them. So if we exchange them, you see that eventually you have H2 with just one of the SO4. So H2 SO4 as the chemical formula of that compound. So it is important to know your know the combining power and the symbols of some common radicals, because they tend to be useful when you need to write their chemical formula. Also, apart from, now let's quickly take a deep dive into the idea of oxidation number. Now, oxidation number, generally, as we have said, to be able to write correctly chemical formula for compounds, a system of small o numbers related to the combining ratio of elements has been developed on the basis of arbitrary rules. Such numbers are what we call oxidation number, okay, or sometimes regarded as oxidation state. Okay, it is the charge assigned to an atom in a compound. So usually it used to be the oxidation number, usually, not all the time, usually is a combination of the valency and the charge. Okay, for example, sodium has a combining power of 1 as its valency, and it has an oxidation state of +1. Okay, chlorine has a combining power of 1, and it also has an oxidation state of -1. Okay, so usually, generally speaking, most metals used to have positive oxidation state, while non-metals used to have negative oxidation state. Okay, now let's look at some general rules that need to be considered when dealing with oxidation state and oxidation number. Now, as we have said, metals usually possess positive oxidation state. Okay, while non-metals usually possess negative oxidation state. Okay, and whenever you have a neutral compound, we have an oxidation state of 0, the oxidation number of a neutral compound. For example, if you have water now, water has no effective charge in this case, so its oxidation number of this compound, water, is 0. H2SO4, there's no charge, it's a neutral compound, so its oxidation state as H2SO4 like this is what? Is going to be 0. What that means is that the oxidation state of 2 hydrogen added to the oxidation state of sulfur, added to the oxidation state of 4 oxygens that are here, will all add up to give 0. That's why we say sum of oxidation number in a neutral compound is always 0. Okay, while the sum of oxidation number in an ion is always equal to the charge on that ion. For example, the radicals that we looked at, let's pick a radical. Now, let's say we have SO4 2 minus as an example. In this case, SO4 2 minus is a charge. So the oxidation state will, if you sum up the oxidation state of oxygen, that is oxidation state of sulfur plus 4 times oxidation state of oxygen, we are going to have -2 as a result. Okay, so these are some very basic rules for deriving the oxidation state of unknown elements within a particular compound. Now let's look at some other very important rule that you need to be familiar with when trying to calculate oxidation number. When trying to calculate oxidation number. 1, generally speaking, free elements and molecules, they usually have an oxidation state of 0. For example, if I said sodium, oxidation state of sodium is 0. nitrogen as it is like this, even though don't let us know, let's say magnesium. Magnesium has an oxidation state of what? Of 0. Also, neutral molecules like or free molecules like oxygen gas, chlorine gas, fluorine gas, and so on like that. They usually have an oxygen state of what? Oxygen state of 0. Okay, monoatomic ions, as we have discussed earlier, the monoatomic ions has an oxygen state of +1. If it's an ion, Na+, that is, it has been ionized, it has lost 1 electron. So it is when it has lost 1 electron, it becomes Na+. In its neutral state, when it is just Na, okay, that it is assumed that it has not lost any electron, then it is 0. But when it loses an electron, it becomes, or when it is in a combined form, it becomes +1 as its oxidation state. Okay, oxygen has an oxidation state of -2 in its combined form. Okay, and except in peroxide, yes, it is important noting that in peroxide, the oxidation state of oxygen is not -2, but what? But -1. Very, very important. For hydrogen, generally, hydrogen also have an oxidation state of +1, except when it is combined with hydrides. When it's combined to form hydrides, usually like metallic hydrides, like when you have substance like calcium hydride, okay, the oxidation state of hydrogen here is not +1, but -1. Also, let's say you have even lithium aluminum hydride, okay, lithium aluminum hydride, we call it lithium tetrahydroaluminate 3. In this particular compound, the oxidation state of hydrogen here is not +1, but it is what? It is -1. Some of oxidation numbers of neutral compounds as well. Just some of oxidation number of neutral compounds are 0, and some of oxidation number in polyatomic ions is always equal to the ion, the charge on the ion. We have discussed that up here. Okay, so let's look at some of the first 20 elements and their oxidation state. The first 20 elements and the oxidation state. Okay, these are some of the first 20 elements and the oxidation state. So looking closely, you see that there's a relationship between the valency and the oxidation state, but not all the time, because there are some compounds or there are some elements that can have more than one oxidation state. For example, if you look closely, you see that carbon can have oxidation state of 2 and can also have oxidation state of -2 and oxidation state of -4. Okay, depending on the case. So these are the oxidation state of the first 20 elements. Also observe that the oxidation state of helium and its family are what? Are 0. Okay, helium, neon, argon, they have an oxidation state of 0, because at ordinary condition they tend not to combine. Okay, so these are some of the oxidation states of the first 20 elements. So it's very important that you are familiar with the oxidation state of some of these compounds, of these elements. Now, these are the rest of the 20 elements, of the first 20 elements. So as we have said, some elements can have multiple oxidation states. You can say like sulfur. Sulfur is up to 3 oxidation states. Okay, and these are as a result of the fact that they can combine in different forms. They can combine with other elements in different forms. So hence giving them different oxidation states. All right. Calcium has an oxidation state of +2, which is very close to combining power. Okay, it's combining power. We have said that time that the chlorine is having an oxidation state, the valency of 1 is combining power is treated as 1. Now, let's quickly look at a typical example of using the oxidation state. Okay, using the oxidation state. For example, let's say let's look at this first example. Determine the oxidation state of calcium in calcium chloride. Okay, determine the oxidation state of calcium in calcium chloride. All we need to assume is that first, calcium chloride is a neutral compound. If calcium chloride is a neutral compound, we can say the oxidation number of calcium chloride is going to be 0. Oxidation number of calcium chloride is going to be 0 since it's a neutral compound. So what does that imply? And we know that the sum of the oxidation number of each element present in a particular compound must give us 0 in this case. So it means that the oxidation number ON of calcium plus 2 times oxidation number, that's ON of chlorine, must give us 0. So we can say let the oxidation number of it's already written here. So first thing is we have to say let the oxidation number of calcium, let it be X. So we only have one calcium here, so it will be X added to 2 multiplied by oxidation number of chlorine is -1. So 2 multiplied by -1 equals to 0. Then we simplify this. You have X minus 2 equals to 0, and you will get X to be equals to +2 as the oxidation number of your calcium. Okay, of your calcium. Okay, so the second example, we have N2O, oxidation number of N2O, of nitrogen in N2O. Also, we have to know that since this is a neutral compound, the oxidation number of N2O itself must give us 0, since N2O is a neutral compound. So it means the sum of the oxidation number 2 times oxidation number of nitrogen plus oxidation number of oxygen must be equal to 0. 2 times oxidation number of nitrogen. So let the oxidation number of nitrogen be X, meaning that 2 times X, okay, added to oxidation number of oxygen is what? Is -2. So -2 equals to 0. So from here, we're going to say that we have 2X equals to 2. And if we divide both sides by 2, you're going to get your X to be what? To be +1. So we say the oxidation state of N2O is what? Is +1. So that's why we name it dinitrogen oxide, or nitrogen 1 oxide. Nitrogen 1 oxide, N2O, or nitrogen 2 oxide. All right, so now examples. Another example 3 now. We have NO3 minus. This is a radical. In this context, we have NO3 minus. I want to find the oxidation state of nitrogen. The same in this case now, we'll say that the oxidation state is this the species has a charge. So it implies that the oxidation number of NO3 minus is going to be -1 because it has a charge. So if the oxidation number of this species is -1, it means the oxidation number of nitrogen plus 3 times oxidation number of oxygen will be equals to -1. Oxidation number of nitrogen, ON of nitrogen, is X. Let it be X. That's what we want to find. Plus 3 times oxidation number of oxygen is -2 equals to -1. So we have X minus 6 equals to -1. Then X equals to -1 plus 6. So our X is what? +5. So that's why this species will be called nitrogen trioxonitrate 5. It is called trioxonitrate 5 ion. So trioxonitrate 5 ion. Okay, so that 5 that we indicated here is the oxidation state of that nitrogen. Okay, so the tri here is because there are 3 oxygen in this species. So these are some elements that have variable oxidation states. Okay, especially some of the transition metals. Okay, transition metals. The transition metals are elements that they occupy from between group 3 and your group 4. You see that there are some elements on the periodic table that occupy that position, and they usually have partially filled d orbitals. Okay, so Copper, for example, has 2 oxidation states. Okay, because this is because electrons can be lost from the inner shell. In a case where electron can be lost from their inner shell, okay, there are possibility of them having variable oxidation state. Okay, so also, even though nitrogen is not a transition metal like the rest of the examples we have here, but because of the fact that its 5 valence electrons can be gained or lost in different ways. So in order for it to achieve stability, so because of this behavior, it can have multiple oxidation states. It can have multiple oxidation states. So these are very, very important concepts in chemistry that needs to be very, very clear, because the foundation of the concept in chemistry is the idea of understanding elements and their symbols. So try as much as possible that you understand how to proceed or how to interact with elements, their symbols, use their symbols to generate their chemical formula, be able to determine their oxidation state, and you'll be on a good ground to proceed in your journey of studying chemistry. So we're going to stop here. So in the next class, or in the next tutorial, we're going to look at a different topic entirely, developing on this concept. So try as much as possible to watch and rewatch, and also share with your colleagues that you think they need to benefit from this topic. And don't forget to like and also subscribe and click on the notification bell so that when I release a new video, you'll be the first to be alerted. So thank you very much for listening. So see you in another class.